So we have learned that a Riemann sum is a collection of geometric shapes, often rectangles, whose area, when added together, approximates the area underneath the curve. So when is this area too big and when is this area too small? This is climb time, and in this video, we're going to analyze Riemann sums and answer that question. When is the area too big and when is the area too small? So we'll start by looking at two factors. One factor is it increasing or is it decreasing? And the second factor is, are we looking at a left endpoint or are we looking at a right endpoint? It turns out that the area is always too big or too small depending on which quadrant you're in. Are you increasing in left endpoint or are you increasing in right endpoint? Or are you decreasing in left endpoint? Or are you decreasing in right endpoint? So which quadrant you're in determines what is true. So let's assume now that we want to find the area between sum A and sum B. And let's say we want to find just two rectangles. We'll keep it simple and do two rectangles. And so if we have two rectangles and we want the left endpoint, that means the left endpoint would be here and would make a rectangle looks like that. And then here, the left endpoint would be here and make a rectangle that looks like this. And so you could see based on those two rectangles that that area is not equal to the area underneath the curve. It's a little bit too small. So this is going to be too small. And we can see that because there's space here that the area doesn't cover. The area we want will go under the curve from here to here. Maybe I could show that with another color here. So the area I want would include this area up here, and it includes that area there. So this area is missing and this area is missing. So the orange part is the area that's missing. And the white part is the area that I'm actually going to be able to find. So the two rectangles would not totally equal the area underneath the curve. The orange part is the part I'm missing. So what if I want to find the same area? This time, I'm going to use the right endpoint. So same area. This time, I want the right endpoint. So what happens is the first rectangle is going to have right endpoint up here. It's going to look like this. And the second one is going to look like this. And you can see that my area of the white is too big. And so the part that would be too much area would be this orange part here, this orange part here. And so in this case, my area would be too big, too big. Okay, so is the area too big or too small? Well, it depends. Is it a left point or a right endpoint for the height of my rectangle? And if you want to learn more about Riemann sums, check out my other variable. My other video. Maybe it's a variable too, I don't know. But my other video where I talk more about what a Riemann sum is and how it's a sum of rectangles. And these sum of rectangles are trying to approximate the area underneath the curve. So you can see at the left endpoint, we don't quite get high enough. And the right endpoint, we get too high. And so the area ends up being too big. So now let's look at a situation where we're always decreasing. So a situation where we're always increasing is going to be like e to the x or an exponential function, something like that. A situation where we're always decreasing could be something like 1 over x. So these functions do exist. And so you can get all sorts of situations where you're always increasing, always decreasing. And let's say we're trying to find the area underneath the curve and we're approximating it with Riemann sums, and we're going to use the left endpoint. So using the left endpoint, this endpoint right here, it would represent the height of my rectangle, and this right here would represent the height of my second rectangle. As you can see, I kind of missed my spot a little bit here. As you can see, my rectangles get too big. So the extra area is right here, the orange part. And so therefore, this one is too big. So the exact opposite of what we got when we used left endpoints when it was increasing. So when it's decreasing, we're too big. And when we're increasing, it's too small. And then you can probably guess what's going to happen next. Again, same area. And now we're going to use the right endpoint. So if we use the right endpoint, it would look something like this. Use the right endpoint, it would look something like this. And then our area is too small. And so it's a little harder to see the too small there, probably because my rectangles are not as good as they could be. But you probably see what's going on. You get the idea. So you can see that this little orange area here is missing. And so in this case, the area would be too small. So you can see the pattern, see what's going on. So if you're trying to figure out, is your area too small or too big? It depends on two things. It depends whether or not your function is increasing or decreasing, but also it's determined by whether or not you're using a left endpoint or a right endpoint. And if you end up using a midpoint, then it's going to be more accurate. It's not going to be obvious whether it's too big or too small. So it depends on how the function is behaving. But in general, a midpoint, whatever it's missing, it's also has extra of. And so those two kind of cancel each other out. It doesn't cancel each other out perfectly. So it might be too big, might be too small. We don't really know. So midpoint is closer to what we're looking for. But it's not obvious whether it's too big or too small. But left endpoint will always be too small if the function's increasing, and the left endpoint will always be too big if the function's decreasing. The right endpoint will always be too big if the function's increasing, and always be too small if the function's decreasing. We know that for sure. So if we get a situation where a function is both increasing and decreasing, and this happens with a lot of functions, happens with parabolas, it happens with sine of x. So this right here looks a lot like sine of x. So that could be sine of x. So if this is sine of x, and I want to find the area underneath the curve, and I want to do, let's just do two rectangles. We'll keep it two rectangles. And so I want to find the left endpoint. Actually, I'll do four rectangles because it's one of the rectangle will have zero area. So I'll do four rectangles, 1, 2, 3, 4 rectangles. And I'm going to do a left endpoint. So if I do a left endpoint, my first rectangle is going to be that high. The second rectangle is going to be this high. So it's going to end up being too small on this side. But on this side, my left endpoint is going to be up here. And so it's going to go like this. And then my left endpoint is going to be here, and it's going to go like this. So what's interesting about a sine of x curve, or something that increases and then decreases, is that it's going to be too big and too small. And so those two can kind of cancel each other out. So the extra area here is this. This is the area that, because my first rectangle has zero height, my second rectangle isn't quite high enough. My third rectangle is too high, and my fourth rectangle is too high. And so because of the symmetry that we get there, a lot of those things will cancel each other out, not perfectly, but they'll cancel each other out. And actually a left endpoint or a right endpoint will give you a pretty decent approximation for the area underneath the curve, because it's increasing half the time and decreasing half the time. And so therefore, whether you use a left endpoint or right endpoint, in either case, the errors are going to cancel each other out. So that's just a quick video explaining how approximations work and whether or not they are too big or too small, depending on whether or not you're using the left endpoint or the right endpoint, and whether or not your function is increasing or decreasing. But as a reminder, the more rectangles you use, the closer your approximation is to the actual area. And if you find both a left and a right, then you can kind of converge in on the area. And the left might be too big, the right might be too small, or vice versa. But you can converge in on the area by getting more and more rectangles. And if you get enough rectangles, the left will equal the right at some point, which actually equals the area. When I say equals, I mean a good enough approximation for what we need. And that's how Riemann sums work.